So hello, everybody. It's 11 o'clock here in Montreal. Welcome to the today's edition of the CMR Journal Club. I think we'll wait for another minute or so. Bettina should join in at any time now. Bettina Bessler, who will moderate today's Journal Club. So just hang in there. And I see already that Manuel, you're already on. That's great. So you can share your screen then, hopefully, with the PDF and get started. And don't forget afterwards to unshare your screen. And as usual, I'm making just use of the time here. Whenever there's a question, there's a chat box where you can put the question in, and then we can read it, but also once the discussion is ongoing, feel free to raise your hand so that we know that there's a question that you can ask a person. And it's an informal presentation, so no slides, and we'll go through it typically within about 10 minutes. And then we'll have a discussion for about 5 minutes or so before we move to the next paper. And Manuel, you have a very difficult task, because when it's about a method like this, you have to find the fine line between not getting too detailed, but still get your message across. So be merciful with us doctors who are not necessarily always on top of the most recent methodology in machine learning, and try to keep it on a level that it still conveys the message, and all within 10-15 minutes. So
I'll try my best.
But I mean, this is not an exam, so we will all whatever we can take from it, we will thankfully do so. So why don't you get started? Bettina, maybe a little bit late. Why don't you get started? So the first paper is called DeepStrain, a deep learning workflow for the automated characterization of, hello?
Of cardiac mechanics, yeah.
Okay, of cardiac mechanics. And it's by Manuel Morales, who will also present as the first author. And it's from the team, including Maaike van den Bomen and Christopher Nguyen. Okay, go ahead, Manuel.
All right. Well, first of all, thank you to you and Bettina for this invitation. I am a big fan of this seminar. So I'm very happy to be able to present some of my work here. And like you said, this is a very technical paper, very lengthy as well. There's a lot of methods that were developed and also a lot of validation that was presented. So I'll try to keep it at a high level and just go over some of the results, and we can discuss later if there's any questions. So we know that the ejection fraction is often used as a left ventricular functional index, but we also know that its value is limited when mechanical impairment occurs without an ejection fraction reduction. Alternatively, we also know that strain analysis can provide a more comprehensive characterization through non-invasive evaluation of myocardial deformation using CNA data. However, although automated segmentation and motion tracking, which are two steps that are necessary for strain analysis, they are available in commercial software. In our experience, we find that manual correction of these delineated contours that are used for tracking is often required. And this can result in significant variations in strain and also make strain analysis very time consuming. So as an alternative, recent studies have shown that cardiac motion estimation can be recast as a learnable problem using deep learning. However, none of the methods that have been proposed to date have considered the accuracy of myocardial strain as a design factor, or have been applied for strain analysis for that matter. So the purpose of this work was to develop DeepStrain, which is a fast and automated workflow that can derive both global and regional strain measures from CNA data. And in addition to that, this paper also provides a comprehensive assessment of the accuracy and the repeatability of the approach. Of course, our method can be found online in the link provided here. So this is the overview of the proposed DeepStrain workflow. And if we look here to the left, we find that the input is a pair of concatenated short ASIC stacks, 2 different timeframes. So the first frame is always at end diastole, and the second frame is always in a contracted state. And so we use 3 unit-like architectures. So we use VCN, or ventricular centering network. We use Carson, or cardiac segmentation network, and we use Carmen, or a cardiac motion estimation network. So VCN centers and crops the input frame, the input CNET frames. Once they're centered and cropped, tissue labels that are generated by Carson are used to build an anatomical model that you see here. And then the motion estimates that are derived from Carmen are used to evaluate strain, as you see here. And the strain values are then combined with the anatomical model to enable both global and regional strain analysis. So for the sake of time, I'll focus to go in a little bit more detail about Carmen and how it was trained and how we optimize this architecture. So we mentioned that the input is a pair of concatenated frames, so frame 1 and frame 2, and that the output are the motion estimates. However, we don't have the motion estimates, the ground truth motion estimates. So how do we train such an architecture? And we do it by using a series of a combination of different functions. So we use an unsupervised loss function that is based on intensity measures. And this is basically a common registration optimization function. We also use a registration loss function that is based on segmentation. So this is basically a supervised function that leverages the segmentations of the input volumes at training time to impose an anatomical constraint on the estimates. It's important to know that the segmentations are only used during training and are not necessary during testing for evaluation. And a third constraint that we use is to promote smooth motion estimates using a diffusion regularizer. So how do we optimize all these parameters that we have here? There's a whole range of selections of anatomical functions that we can use. Once we know what anatomical function we want to use, we still have to optimize these hyperparameters. And we don't know how to do so in a way that will yield the most accurate and reliable strain estimates. So to do that, we use the automatic cardiac diagnosis challenge dataset for training. And this consists of 150 subjects evenly divided into 5 groups that include both healthy and patients with cardiovascular disease. So one of the heuristics that we use is that we wanted to minimize the variation both between training and testing sets, and also the variation in strain within healthy subjects. So we took this ACDC data set with 100 subjects, and we divided it into 2 groups. And so we trained the network using 50 subjects, using a variety of different anatomical constraints and parameters. And we asked the question is, what happens when we test it? And we only look at the healthy subjects. So for example, in the figure on the left, we see circumferential and systolic strain. And we see the training and the testing set, and this only includes healthy subjects. And we see that there is some variation both between the training and testing set, but also within the healthy subjects. This is especially so in the radial strain. If we use, for example, anatomical constraint, different functions will vary. And so one of the heuristics that we selected was to minimize how much strain varies within healthy subjects. This is on the assumption that the strain should be relatively similar within a healthy population. In addition to that, we also train the network, and then we generated synthetic motion. So train with real health on simulated data. And then we took a look what happens when we change different parameters for the regularization or smoothness, the anatomical constraint. And what we found is what we suspected. We know that increasing the smoothness can improve the quality, the accuracy of the motion estimates. As you see here, in red is the ground truth, and in black is the predicted. And what we want to achieve is more aligned vectors here. And further increasing the anatomical constraint results in better alignment between these two. And we quantify this by looking the difference in the motion estimates, quantified by the endpoint error shown here on the left. And this is us trying to figure out what are the optimal hyperparameters that will yield the most accurate motion estimates. And what we found here is that there is an optimal value somewhere around 0.5, and also with a smoothness of 0.1. This is also reflected when you use those motion estimates to calculate strain. And so we find that there is an optimal way to find the hyperparameters to minimize the bias in the myocardial strain. And so in this manner, we selected both the architecture, the type of loss functions that we use, and also the hyperparameters. And then finally, we trained the neural network, and then we proceeded to evaluate. So how do we do that? Well, we used 15 healthy subjects that had both CNET and tagging data. And in addition to that, the tagging data contained landmarks that had been previously tracked by two readers. And so landmarks were defined in different regions of the myocardium. They were manually tracked. And so we deformed these landmarks using the predicted motion estimates from DeepStrain. And then we calculated how far apart were these deformations. And of course, a perfect alignment would mean that the motion estimates would be perfect. And we also compared this to both tagging-based methods for motion estimation and CNET-based methods. And what we found is that our method was comparable to other CNET-based studies, but important to highlight that our method operates with 2 orders of magnitude faster relative to the other methods. Now, what significance does this difference in the motion estimates have on the strain values? So we selected the method with the best performing metric based on the endpoint error on the motion estimates, and we calculated the myocardial strain. And then we compare it to that derived from our method. And that's what you see here on the right. And you see that both methods are quite comparable for global, circumferential, and radial strain, although there are some expected differences on the strain rate. And here you see the quantification of the global strain between the tagging and the CNET metric. And what we found is that there was no significant difference between these two approaches. We also recruited 10 healthy subjects, and these healthy subjects were underwent repeated examinations within the same date. This is some illustrations of different subjects for global strain for both circumferential and radial, and also strain rate on the left. And on the right, you see a quantification of regional strain. On the top, you see the relative change average over all the subjects, and at the bottom, you see the absolute relative change. And what we found is that suspected circumferential strain was much more repeatable than radial, but it was quite repeatable. In most segments, it was less than 2% in strain. And when we compare all the global parameters, such as global and radial and systolic strain and strain rate, we found that the relative change all across all parameters were very low, inconsistent with what has been reported in the literature and in some of the best studies. So there are some limitations within this method, and there's a lot of work to be done if anyone is interested in pursuing this approach. So I think the most obvious one is that we were not able to calculate longitudinal strain. And this is mainly because at the time, the training data that was available did not include the long axis information. But this could, in principle, be readily applied if such data set existed. In addition, we only use 150 subjects for training, and it could potentially be a larger data set. I know larger data sets are available. It is unclear to me that we need larger data sets, and perhaps the ones that we use is sufficient, but it requires further validation. And another limitation is that we didn't really quite validate whether the heuristic that we use in minimizing the strain values within healthy subjects will lead to truly accurate strain, and it could actually be the opposite. It could potentially prevent the identification of subtle disease because you might lose some sensitivity to abnormal strain because you're trying to minimize that. And further, we did not assess the repeatability in patient populations. This was only shown for healthy subjects. And so in conclusion, we developed an end-to-end learning-based workflow for strain analysis that is fast. It's 2 orders of magnitude relative to other techniques. It's fully automatic. It doesn't require any operator. And is based on real-world data instead of making explicit assumptions about myocardial tissue properties or geometry.
Thank you very much. That was, of course, quite a ride for the people like me who are not that much into the technology. Anybody who has questions, please put it in the chat box. So for me, so if it's about strain, what criteria actually, so for just to have a basic understanding, so there's the echo approach of using speckles, inhomogeneities in the tissue. There is the purely deformational aspect with so-called tissue tracking, and then there's the tracking where the deformation is actually derived from the motion information itself in the MR. Which one did you use to inform the machine learning algorithm for basically as basic criteria?
Right. So I think this is more akin to a feature tracking approach, where when we track the myocardial wall boundary, but in this case, because we have access to a more computationally efficient approach, we're able to calculate the tracking of all the pixels within the myocardium. So thanks to that, we're able to provide dense information for the entire heart instead of just a global value.
Yeah. Okay, and the other question I have, and then we'll have to move on to the next one. To what extent do you think this method would allow to generate maps that also provide specific information on the various regions? Because the various segments in the heart, or regions, or you want to call it, they have quite different strain values, and also for each of the 3 strain values you have different, and this may, even between healthy volunteers, it may differ in, for example, their thoracic habitus, the position of the heart. So that also relates to the question of the sample size and whether we need samples that are specific for ethnicity, sex, and all that. So that is the other question I had is, do you think we need more studies that are specific to ethnicities and sex and similar markers?
That's a really good question. So I think it's unclear exactly what is the target data set that we would need to reliably measure strain. The data set that I use contained perhaps not a very large data set, but it was a very heterogeneous group. So it contained different pathologies such as hypertrophic dilated cardiomyopathy, patients with myocardial infarction. And so perhaps not necessarily a larger data set, but more heterogeneous data set is what would be the best. What our initial results on looking at regional strain, we found that in some of the cases, like as you see here, the reduction in strain in regional strain was well correlated with the locations of myocardial infarct on the subject that we tested, for which we know where the myocardial infarction was. So that is promising, but I think the further stories should be warranted to determine in a more prospective manner whether that correlates to locations of motion abnormality, whether that be by echo or by MRI, or even, for example, to see whether they are associated with the location of by LGE.
Okay, thank you very much.
Improvement is needed.
Yeah. Okay, thank you. Well, we have to move on in just some time, and I'm happy to now hand over to the host of today's Journal Cup, Bettina Wessler, and it probably others ran into the issue before, like we did before last year, that the time zone difference, usually 6 hours between Eastern and Germany, but it's now not 6 hours but 5 hours because Europe already moved to the basically the winter time, which I really don't like. All the problems that are associated with that probably are worse than what we gain. So Bettina, take it over from here.
Yeah, so really big sorry from my side. I really didn't think of this time zone difference getting smaller, actually. So we actually have 4 p.m. instead of 5 p.m. But yeah, so thanks
for the next 2 weeks, and then I think then we're back to 6 hours, but for 2 weeks.
Okay,
yeah.
good to know. Okay, so yeah, thanks very much, even for joining us today. We have our second paper, which is really exciting and interesting as well, published in Radiology on free breathing accelerated cardiac MRI using deep learning, and it's a validation study in children and young adults. So the floor is yours. I'm looking forward to your presentation even.
Yeah, thanks very much for the introduction. I'm Evan Zucker. I'm a clinical radiologist at Stanford. I focus in primarily pediatric congenital heart disease. This was a collaborative study between our radiology department, engineering department, and also GE Healthcare. So kind of continuing the deep learning theme, as this audience is well aware, particularly in children and in young adults, cardiac MRI exams can be obviously quite onerous due to the requirements for multiple breath holds, and it's clinically difficult oftentimes to get patients through a long exam. So obviously there's been a number of different approaches to both speed up acquisitions as well as image reconstruction over the years, including compressed sensing and other methods. So more recently, there's been work in artificial intelligence and deep learning specifically to combine deep learning techniques with highly accelerated sequences to produce comparable images while sampling less of case space effectively. There was one paper out of UCSD in which they produced essentially super resolution MRI images from training data with low matrix size. So recently our group took a different approach. It's described in more detail in a previous publication in Magnetic Resonance Imaging in Medicine by Chris Sandino, who's an electrical engineering PhD student. But basically, the approach is to combine a highly accelerated 2D cine cardiac MRI sequence with a deep learning reconstruction method that works in a case-based domain. And I'll go over that a little bit. And so the goal of this study was basically, number one, to further optimize the deep learning reconstruction technique and the accelerated cardiac cine sequence, and then to validate it in a cohort of children and young adults. So, without going into a lot of detail, how did the deep learning reconstruction method work? So unlike, many machine learning reconstruction methods, our method works in the case-based domain. So it's a kind of a model-based or physics-based algorithm. And basically, essentially, the inputs are coil sensitivity maps and calibration regions. And the model works basically by applying deep learning methods to determine the weights for the Spirit reconstruction method. So this is a previously described method, Spirit, published by Nikki Lustig and colleagues at UC Berkeley. And it's basically a auto-calibrating parallel MRI approach to reconstruction. So, traditionally the weights for this reconstruction method are, determined using mathematics and linear algebra. So, in contrast, this technique that we use basically uses deep learning to determine the weights for this model. So that's why, we're kind of using the term physics-based model. And because it's based on the underlying physics, it's we think less dependent on the underlying training data. So basically the reconstruction method was trained on a cohort of 22 healthy adult volunteers. This data was supplied by GE Healthcare, so it's not available for public use, although anyone who signs a research agreement with GE Healthcare, they're willing to make that available. So basically it was trained on 10 subjects, and then 2 subjects were used for validation and 10 for internal testing. And then, so the second part of the work was basically developing this 12-fold accelerated SSFP sequence. So again, that was modified from a prior prototype. One of the main issues that we saw in our previous prototype was that we were getting a lot of these dark band artifacts. So basically, the phase encoding setup was modified to help mitigate some of these artifacts. And that's described more in this figure that I can refer you to. So then, in the second part of the paper, basically we have modified the reconstruction algorithm and fine-tuned the accelerated cardiac synase sequence. So then we recruited a prospective cohort of 50 patients, pediatric patients and young adults. This was primarily based at our children's hospital, who underwent both the traditional SSFP sequence as well as the accelerated synase sequence with deep learning reconstruction. So you can see the summary of the patient characteristics here. Most of the patients were, in the teenage age group. A few patients were greater than 18 years old. We do see some adult patients at our children's hospital, a bit more males than females, and about an even split in terms of cardiomyopathy and congenital heart disease cases, which kind of, span the spectrum from tetralogy of Fallot to single ventricle disease. Most of the studies were performed awake. There are a few under general anesthesia, and most were performed at 1.5 Tesla. The majority of studies were performed non-contrast. For our congenital heart disease studies, we do utilize pheromoxetol sometimes. So in those patients, they get pheromoxetol before the scan. So in some of the patients, they had ferraheme on board, and most scans were done breath held. So basically, for every case, 2 radiologists scored the overall image quality of the traditional SSFP and accelerated synase sequences, and then they manually drew the contours to figure out the volumes and ventricular mass. We also used an automated contouring software, the Arteris platform, to get automated volumes as well. So in terms of the image quality criteria, basically scored on a 1 to 5 Likert scale, 3 being adequate image quality. And we also scored the volumetric mesh data sets that were generated by the auto contouring software. To give you an idea what that means, basically the auto contouring software will basically generate a volume corresponding to the left and right ventricle. So we scored, the degree of distortion or lack thereof in terms of image quality. And then, so basically the second part of the analysis consisted of looking at the inter-rater and inter-rater reliability of volumetric measurements between readers and also between techniques. So SSFP versus, versus the accelerated Cine sequence. And that was evaluated using interclass correlation coefficient as well as Bland-Altman analysis. So this is a figure just showing some examples of relatively comparable image quality between the SSFP sequences on the top and the accelerated Cine sequence images combined with deep learning reconstruction. These were in end diastole. Obviously, these are Cine images, and functional images are available as well. So there is some loss of detail in certain areas, but kind of the overall image quality was similar, and more importantly, the volumetric measurements were quite similar, even though there's slight loss of detail in certain areas. And then just interestingly, again, as I mentioned, there were a few single ventricle cases in our cohort. And you can see that the deep learning Cine reconstruction method actually was able to produce pretty good images, despite never being trained on single ventricle disease. And that's probably, again, related to the fact that this was a physics-based reconstruction algorithm, so less dependent on the images that were used for training, which was a cohort of healthy adult volunteers. In terms of scan time for the DL Cine sequence, scans were performed on average in about 0.9 minutes. Compared to the traditional Cine sequences that were about 3 minutes. And when we accounted for the time for breath holding and recovery, the time for the SSFP sequences to be performed was on the order of 10 minutes. And again, if you account for the time for patients needing to take a breath and then recover and stuff like that, it can be quite time consuming. The overall image quality was just slightly lower for the DL Cine sequence, 3.8 out of 5 compared to about 4 for the SSFP. And that was statistically significant, although probably not clinically that important. All the scans are rated at least 3 or diagnostic level. And then, based on the feedback from some of the reviewers, we did some subgroup analysis in terms of higher and lower heart rates and, Barahim enhanced scans versus not, and didn't find many differences. At the request of one of the reviewers, we did try to evaluate whether one sequence or the other was better in terms of assessing wall motion. And, we didn't find a statistically significant difference, but there was really essentially no wall motion abnormalities in either, in the cohort. So it's not really accessible by this technique. There were, some examples of, more clearly worse image quality with the DL Cine approach, which I pointed out here. There were some distortion artifacts, and you can also see some substantial susceptibility artifacts. Again, if you were contouring the ventricle, this probably wouldn't, affect things too much. But if you were looking for a subtle wall motion abnormality, that could interfere with things. So the second part of the analysis is basically looking to correlate, basically whether the ventricular volumetry data and mass were comparable. There's a lot of supplementary appendixes looking at various subgroups, but overall, the interclass correlation coefficients for the ventricular volumes and mass on the left and right side were quite good. These are the composite interclass correlation coefficients for LVE, DV, LVESV, et cetera, and all, at 0.76 or higher. So, in a good to excellent range. And this was similar both for the two human readers as well as the auto contouring software in which the contours, were not manually adjusted. So there's a high degree of fidelity there. And, finally, just we did bland Altman analysis as well. Within the limitations of the paper, just the left ventricular volume results are presented here, but all the right ventricular volumes, et cetera, are presented in the supplementary appendices. So you can see that comparing the SSFP to the DL-Cine technique, the mean difference, for example, in left ventricular volumes was close to zero, basically in all the left ventricular measurements. And the limits of agreement were, within the range of plus or minus 20. This is in absolute ml, 15 to 15, and the ejection fraction plus or minus 10%. So, in a reasonable range. So in summary, in this cohort of 50 children, basically, the acquisition time was quite a bit faster with the DL-Cine technique, 0.9 versus 3 minutes, and only slightly lower image quality, and good to excellent agreement in ventricular volume and mass results between the two groups. So where does that leave us? We have incorporated this DL-Cine sequence into our clinical practice, and with our ongoing collaboration with GE, the goal is to basically develop this into a product sequence, actually. So at the present time, we do utilize the DL-Cine sequence, and because the images come back in relatively real time with our setup, we can review them, and if they're adequate, then we don't need to go on and do the regular Cine sequence. So this study, did have some limitations, as was noted in the previous presentation. Obviously, the training data set was relatively small, consisting of 22, adult volunteers. As I mentioned, because it's a physics-based model, it may be less dependent on the actual number of studies. And, there's certain other things that we could assess in more detail. For example, more, segmental image quality. We didn't look at things like strain analysis, et cetera, as in the previous presentation. And it was a relatively heterogeneous cohort. We did do some subgroup analysis in terms of congenital heart disease versus not, et cetera, and didn't find major differences. But obviously, even with 50 patients, the numbers are rather small. So, so in summary, this approach was very promising and, produced, comparable volumetric results. And, we're hoping with continued use and collaboration with GE that this can be, put into practice more widely clinically. Thank you.
Thank you very much, Even. This is really impressive work. So I personally, and I think Matthias too, we're looking really forward to see larger patient cohorts, because I was wondering whether we saw this a bit less detail in the scenes, which might maybe burden some morphological information, which could be relevant for especially cardiomyopathies or diseases where the morphology of the myocardium is really relevant to see. I'm really looking forward to seeing this sequence applied in these different patient cohorts, but you actually chose a very difficult patient cohort to evaluate and validate your sequence. So congrats for this work. I have just one quick question because we're quite advanced in time. Did you think of using the information you have due to this this physically based deep learning model to also incorporate an automatic segmentation, so to combine your model with another one, so that you don't have to post-process the images?
Yeah, so basically, so we have a different software package that we're using, the Arteris platform, which does have some auto segmentation built into it. It's not like totally reliable, but so the goal of this project wasn't really on segmentation, but I mean, the hope is in the future, and we're also kind of doing some ongoing work in like auto prescription of planes. So like, we'd like it to be, like auto scan the patient, do it in the fastest time possible, and then auto segment the, so we try to take away all these, manual steps as much as possible. So I think it's just a lot of exciting things that we can accomplish, and sometimes getting things together is difficult, but one thing at a time, and hopefully with a lot of progress. Yeah.
Evan, maybe you can combine it with DeepStrain to get the automatic
yeah, exactly.
and train all in the scanner. It's open source.
right.
That's actually the vision, to combine all these networks together into one thing in the end, or stack them each above one another, and then fully automate the entire pipeline. But we are not there yet, I guess.
Yeah.
Okay, so I don't see any questions in the chat. So I'd like to quickly hand over to Matthias for a quick preview for the next Journal Club.